Welcome to the Explainer. Today, we're diving into something absolutely wild. We're literally prying open a 2,000-year-old mathematical cold case. For centuries, we've treated prime numbers like these irreducible, totally unpredictable atoms of math. But what if everything we assumed about how they're distributed is just flat out wrong? What if we've just been looking at them from the completely wrong angle? We're going to explore a massive paradigm shift today, one that redefines prime distribution as a stunning, multi-dimensional symmetry.
Think back to that flat, one-dimensional number line we all learned about in grade school. For generations, that simple little line has practically forced us to see the gaps between primes as erratic, totally random jumps. But let me ask you this. What if that standard number line is actually just a restrictive geometric illusion? What if it's masking a much deeper, beautiful, and completely deterministic structure?
Section 1. The one-dimensional illusion.
So, the analytic problem hits us right away. On one side, we've got the 1D chaotic number line. When you try mapping primes on a flat line, honestly, they just look like static noise. It forces us to hunt for these localized, repeating interactions that, well, they just aren't there. But then look at the other side. 2D harmonic space. This is where primes finally reveal themselves, not as random noise, but as a global analytic structure governed by pure determinism. Squeezing primes into a single dimension literally creates a mathematical stall point where analytic proofs just completely break down.
And, ma'am, that 1D stall point is a huge problem. The gaps look totally erratic, and you randomly hit these massive numerical prime deserts, where primes just completely vanish. Because relying on that linear timeline is so flawed, even modern machine learning heuristics fail to predict them. AI is built to search for localized statistical variance, right? It looks at immediate neighbors. But here's the thing, prime numbers couldn't care less about their immediate neighbors. They're governed by a massive, overarching global structure that dictates the entire number line all at once.
Section 2. Bending the number line. Okay, so how do we escape the first dimension? We use a mechanical three-step process to physically bend that line into a two-dimensional polar map. First, we find the gap between consecutive primes. Second, instead of just plotting the gap, we calculate its reciprocal radius. So a larger gap actually gives us a smaller number. And finally, step 3, we spin that point by an irrational angle, specifically the golden angle. That irrationality is key because it ensures every single prime finds a totally unique, non-overlapping home on the plane.
Now check out the physical result of doing this. Look at how tight prime clusters, your 11s, 13s, 17s, 19s, they aggressively push outward toward the perimeter. Why? Because their reciprocal gap is a larger fraction. On the flip side, those massive gaps and prime deserts generate tiny fractions, which mechanically forces them into this dense, tight central core. It's like watching chaos organize itself into a perfect, macroscopic pattern right before your eyes. There's a quote that perfectly captures this paradigm shift. By shifting our perspective into the complex plane, we find that the perceived chaos of the number line is actually a one-dimensional projection of a much larger multi-dimensional symmetry. So the primes aren't random at all. They act like this rigid mathematical skeleton, forming a highly organized structural order that was just totally invisible to us from a 1D vantage point. Section 3. The geometric architecture. So, enter the divisor function. This function takes our standard integer number line and literally transforms it into a physical geometric space. Think of it like a topographical map. In this discrete scalar field, highly composite numbers, the ones with a ton of divisors, they actually act as towering peaks in the terrain.
And then, nestled right alongside those peaks, we have our primes. Because prime numbers possess a minimal divisor count of exactly 2, just one in themselves, they act as the minimal energy valleys of this landscape. It's best to think of them as the natural grooves in the terrain that perfectly guide the geometric flow of mathematical data. Now, as we map all this out, things get even crazier. We hit the Fibonacci dimensionality split. As the sequence grows and hits Fibonacci milestones, like 5 or 13, the system actually resets its algebraic base. To keep distributing these points evenly, the 2D map is mechanically forced to fold up into 3D cubes and eventually into 4D hyperstructures. This routing geometry stabilizes across multidimensional space, basically proving that primes are the immutable anchors holding the entire universe of numbers together.
Section 4. Shadows of a hidden wave. I've loved this metaphor from the source material. If we use the metaphor of light and shadow, Primes are not the glowing source, they are the shadows cast by a hidden, deeper frequency. Let that sink in. Primes aren't these physical objects generating chaos. They're actually the visible, physical readouts of a deeper, pre-existing spectral environment. They're just the surface ripples of a hidden wave.
To actually measure this hidden wave, researchers are throwing out the ruler and pulling in audio engineering tools, like the Hilbert transform. Instead of focusing on the amplitude, the height of the numerical oscillation, the Hilbert transform extracts a continuous phase coordinate. We shift our entire focus to the latent rhythm and timing of the prime sequence, filtering out the noise to find that fundamental frequency. Statistically speaking, this reveals that primes behave as what's known as a Cox process. In a Cox process, events are never independent. Instead, they're governed by a fluctuating background environment, a mathematical topography that's constantly shifting and dictating the odds of an event even happening. So prime numbers are mathematically favored to cluster in specific regime zones, based entirely on this invisible background wave. And what is that background wave? It's the zeta-zero symphony. The spacing of the non-trivial Riemann zeta zeros acts as specific invisible wave frequencies operating within log space. When these invisible spectral waves overlap and constructively interfere with each other, boom, a prime number emerges right into our reality. The numbers we observe every day are literally just tracing out a structure that already exists. Section 5. Routing the future of AI. So what does this mean for the real world? Well, by mapping network routing constraints to these exact prime symmetries, researchers have developed a completely new computational primitive, a continuous coordinate map integrating into a discrete Riemannian metric tensor. If that sounds like a mouthful, the simpler version is this. This complex math completely replaces random localized AI guessing with a highly efficient, collision-free highway system that is guided strictly by prime architecture. And the empirical wins here are just staggering. The R4 rotor exploits angular non-uniformity using a fixed 4D hop fibration map, which practically eliminates AI path collapse phenomena. We're talking success in 99.4% of trials. Plus, it delivers a 45% wider spectral gap compared to standard transformers. And check this out, its routing compute footprint scales sublinearly at k to the power of 0.572, instead of the heavy linear k to the 1.0 we see in standard models. It's a massive testament to the sheer efficiency of deterministic prime symmetry. Now, to actually make this work at scale, the router has to maintain thermodynamic stability. It perfectly balances discrete graph adjacency with continuous hyperbolic distance. By ensuring that the math, specifically the sum of the manifold's Ricci curvature and the Hessian of the potential field, remains strictly negative, it guides these massive data packets through vast computational search spaces without any coordinate drift whatsoever. We've seen how primes bend from a flat line into stunning multidimensional symmetry. We've seen how they act as acoustic shadows of hidden waves and how they are literally routing the future of AI. So I'm going to leave you with this final thought to ponder. If prime numbers are simply the geometric shadows of a continuous spectral wave, is the universe of numbers we use every single day actually just the physical manifestation of a hidden geometric resonance? Thanks for joining me for this explainer, and definitely keep questioning what you thought was just random noise.